Okay, welcome to part 2 of our review on chemistry and atomic structure for materials for studying matter in material science and introduction to engineering. We learned in the previous video that electrons can be located in orbitals such as s orbitals. And when we think about these atoms and their electrons in these orbitals for establishing bonding, we need to consider how these orbitals interact. So in the case shown here, we have an example of forming the hydrogen 2 molecule from two hydrogen single atom structures. And as we bring these atoms closer, we can consider the implications on what happens to these orbitals. So as noted in this structure here, I've indicated a hydrogen atom with a single electron. So our electron configuration would tell us we have a 1s1 electron configuration in each of these hydrogen atoms, and therefore neutral because of the 1 electron, 1 proton in the atomic structure. And the s orbitals have matched phase, so the sort of phase of the three-dimensional wave, that is the electron orbital, is the same, that is, it is positive in amplitude. If you go to a one-dimensional wave analogy, you can think of the phase being the positive territory above a wave curve, like a sine curve or something. So the shading here indicates that these s orbitals have matched phase, and they can constructively interfere and add those positive amplitudes together to make a new orbital structure. So as we bring these hydrogen atoms closer together and consider the hypothetical of making a hydrogen molecule this way, we can see how there would be constructive interference because of the matched overlap between positive phases of the s orbital, and this overlap leads to constructive interference, and we build more electron density between the nuclei of the hydrogen atoms in the H2 molecule. Okay, so here we end up with a axis through the H2 molecule as shown. The axis bisects the two nuclei of the hydrogen atoms in the H2 molecule, and this axis is along the along the minimum distance between the two nuclei, and that would be what we're used to considering as the H-H bond in H2. You can see the electron density is symmetric about this axis, with most of it concentrated between the two nuclei where we had that positive overlap. Okay, so when we have symmetric electron density about that axis that joins the two atoms of the bond together in this covalent bond, we call this a sigma bond. So this is the sigma bonding orbital that has resulted from two s orbitals coming together for the H2 molecule. Okay, let's just clean this up a little bit to make room for some of the next content. Okay. Okay, so moving forward, and we remind ourselves of the carbon that we covered in the previous video. We'd like to see how we can learn how carbon makes similar type bonds. So we saw before the electron configuration for carbon was 1s, 2, 2s, 2, 2p2. And that's reflected down here for the energy diagram for the electrons in that electron configuration. Here the half arrows indicate one electron, so one electron here, another electron here, and you can see that the two electrons in the 1s orbital are indicated with these two half electrons of opposite spin, pointing up and down respectively. Okay. But if we know that carbon likes to make 4 bonds in many of the materials that we'll study in this course, including polymers, the bonding model here isn't, the orbital model here for the carbon atom isn't set up to make 4 bonds. If we're to share electrons between carbon and its bonding partners, it looks like we have the opportunity to really only share 2 electrons and establish 2 bonds in carbon. but carbon usually makes 4 bonds. So something needs to adjust here. Take, for example, the carbon in and hydrogen distributed in methane. We might consider these single bonds as formed from carbon with 4 electrons available and the hydrogens each with their own electron available from the 1s1 configuration, analogous to what we saw in the H2 molecule a moment ago. So as we would bring these centers closer and closer together, we might end up making a 2-electron shared single bond by a similar manner. But this current view is not aligned with the atomic structure that we have from the electron configuration. So additional models are needed to describe this. And so the quantum mechanics tells us that we can redistribute these 2 orbitals into hybrid orbitals because they are so close in energy. And so this is the idea of blending, quote unquote, mathematically through quantum mechanical calculations, these orbitals into 4 new ones. So 3 p orbitals come together with an s orbital, and we will end up with 4 equally matched orbitals that are hybridized to establish sp3 hybrid orbitals. Okay, and so these are all the same. They're all degenerate in energy. They lie on the same energy level here, and this hybridization is possible from the quantum mechanical handling of these atomic orbitals because they're close in energy. Okay, so we'll often describe covalent bonds and recognize the geometry of the centers and use that to predict what type of hybridization justifies the bond angles and the bond sharing that's occurred. Okay, so with that idea, we can see here that in our principal quantum number of 2, that we can expect the s and the p orbitals to give us new options. The previous slide I showed you how we might end up with 4 degenerate orbitals, all labeled sp3 orbitals, if we take the 3 p orbitals and the 2s orbital and blend them together. We can also do this and leave behind unused p orbitals as some other options. So option A we covered on the previous slide. Option B and option C can also be done to generate new hybrid orbitals, provided that we leave a p orbital untouched. And this it can help us explain bonding involving multiple bonding at a carbon center, for example. Okay, so given where we were before with atomic orbitals, we saw that there are s, p, d, and f orbitals at certain principal quantum numbers. And when we consider the idea of hybridized atomic orbitals to lend to the geometry and the covalent bonds that we often see in materials, we have hybrid atomic orbitals now. So in those listed here would result from hybridizing s and p orbitals with a given number of p orbitals to give us a certain options. Okay, hybridization with d orbitals is also possible, and even hybridization with f orbitals is also possible, but we won't see that in this course, and that's for other more advanced courses in chemistry. So hybridization, to sum, it results in better orbital overlap to form bonds, such as covalent bonds, and the result of this is a better overlap, and the description of this establishes why we see strong bonds for these covalent bonds. Strong bonds also are synonymous, quote unquote, with shorter bonds. So the stronger the bond, the shorter it is. Okay. And we covered this for hydrogen when the resulting molecular orbital, where we brought together atomic orbitals or hybridized orbitals with other hybridized orbitals or hybridized orbitals with other atomic orbitals, and the electron density is symmetric about the axis that joins those two nuclei together, we have a sigma bond. Now, when the electron density is not within the axis joining the two nuclei together, that is, there's some electron density above and below that axis, we have pi bonds. And in certain cases, you can generate non-bonding orbitals as well. And